Hello everyone, I'm Andrei from EVM, and today I'll talk about very hacky stuff, and it's funny that it comes after Rust security presentation. I will do everything that you shouldn't do. Okay, I will start with a short Solana introduction because I don't know how many people are familiar with the Solana concepts. Basically, a Solana transaction has one or more instructions. Each instruction calls one Solana program and has a list of account inputs and also a byte array as an instruction input. An instruction also can call other instructions of other programs as part of its execution through a mechanism called cross-program invocation. It's basically like in a normal runtime where you call another program from yours. Solana accounts also have a data field containing a byte array that we are going to exploit next. And Solana programs are basically just Solana accounts where the data field contains Solana bytecode. Also, native Solana programs are programs that are deployed at predefined addresses and are implemented as part of the runtime itself, for example, like the Solana system program. Let's talk a bit more about the Solana program runtime. So as I said, Solana programs are compiled to ELF shared objects containing Solana bytecode. And this bytecode is a variation of the BPF bytecode, Berkeley Packet Filter. The SBF bytecode is interpreted by the Solana virtual machine and sometimes also JIT compiled. And let's look a bit at the address space of Solana programs. The address space of the Solana programs in the VM is fixed, and it has 4 important addresses: the program code, memory segment, the stack data memory segment, the heap data, and the one that we'll focus on next, the program into parameters. In general, when I'm going to talk about the addresses, I'll just say the non-zero values so I don't spend too much time on describing the address. Let's talk about the memory layout of Solana program input parameters. Basically, starting at this address over here, we have a list of accounts that are serialized in a binary format. We have the number of accounts at the beginning, then an application marker because you can have multiple accounts that are can refer to the same byte array, and you can just use a ref cell to refer to that again. We have a few Boolean fields: if it's a signer for the transaction, or if it's writable, if it's executable, the account, the original data length of the account, the pub key, the owner, the LAN ports, and the length of the data field. There are also some constant asserts for this computation, so you can see that these values are constant and what their value actually is. And the important takeout from this slide is that the address of the first Solana account in a transaction is fixed, and it's only always this value, 46. And we are gonna exploit this in the next slides. There is a nice assertion that you can write at the beginning of any Solana program that has at least one Solana input account, and it will be always true. It is the one here. Basically, the first account data field, the address of that data field is the one that we discussed before. Only the first Solana account upholds this constant address property because the other accounts have a different offset depending on the length of the data field of the first account. And you can verify this either by deploying your smart contract on any chain or by using Solana program test, but with a caveat: you should use Solana program test with an SBF shared object and not with a natively built program like on your local machine, because the Solana, of course, your local environment does not respect the Solana SBF ABI. So, yeah. Yeah. It's just, no, it's not, I mean, it's just... Can I just kind of like check if this account already exists or not? You can use it, I mean, it's not mandatory, but it's just, let's say, game of showing that the Solana runtime has a very fixed memory model. I mean, there is no address space randomization as it happens in normal operating systems, because you are in a VM and all the addresses for some data are fixed. Like the heap is always in the same place, the stack and everything. It's just like a proof of concept more, let's say. So as I said, we have a memory region at the fixed address which is mapped to the data field of a first Solana account in an instruction. And actually, if you use the same Solana account as input for two different instructions in two different transactions, you actually are able to persist the memory region of the Solana runtime across transaction boundaries, if you want. You shouldn't do that, but let's see what we can do with it. What do you say if we put our heap there? And I'm gonna say why we at the EVM are trying to do that. Basically, the idea is also doable in an operating system theoretically, but it's not simple. As I said, it's basically the idea of memory mapping a file to a memory segment where you put your heap, and save it to a file, and then reuse the heap for the new for multiple program invocations. But it's not easy to do because any modern operating system has address space layout randomization, which just changes the start address for important program segments each time you restart your process. The Solana program heap. Let's talk about it, about the normal heap that the Solana program has. So the memory region for the heap is, it starts here at this address. The default size for the heap in Solana is 32 kilobytes. And also the default allocator that the Solana Rust runtime defines is a bump allocator that doesn't support free or real locks, so it leaks memory. You can increase the size of the Solana heap up to 256 kilobytes by using a special instruction in the transaction where you want to increase the heap for the rest of the instructions, and that one is the request heap frame instruction. And also, Solana programs may implement a custom heap based on the program-specific needs using the global allocator mechanism. Yeah.
Why do you limit the heap size? Why not just allow like a large heap size? And what impacts does it have?
Solana, in general, I've seen that they have multiple compute budget limits. These are compute budget limits that are limiting how much a transaction can compute. And they have some limits that are by default not very big, but you can increase them without any cost for up to some upper limit. I don't know, is their decision probably to not force the runtime to allow a lot of data from the beginning, even if it doesn't use it? I think it would be the idea behind it. And as I said, we can define a global allocator, a custom allocator for us using the global allocator attribute. This is the, let's say, the recipe of doing this in Rust in general. You define your struct for your allocator. You implement the global alloc trait for your allocator, which is an unsafe trait. Has two important methods, alloc and dealloc. You install the custom allocator using this attribute. It's important not to install this allocator when you're not on Solana. If you want to compile, in general, Solana programs can be compiled both for your local let's say SDK that interacts with smart contract, and also as a Solana program. Of course, you want the allocator to be only run as part of the Solana runtime. And we are using a custom allocator in Neon EVM from this crate, list allocator crate. So the conclusion about the Solana program heap, it can be increased from 32 to 256 kilobytes. And in our Neon EVM case, the need for a persistent heap, as I said, comes from the Solana compute budget, because this compute budget also limits the number of the amount of computation that you can do in a Solana transaction. And the compute units for a Solana transaction, the limits are this here. The default limit is 200,000 compute units, and it also can be increased with an instruction like set compute unit limit to 1,400,000. And what are compute limits? Compute limits are some numbers that are associated with each basic instruction of the Solana EVM. Solana VM basically is similar to the EVM opcode gas price. Okay, so why does Neon EVM need a persistent heap? Neon EVM is a Ethereum virtual machine which is implemented as a Solana program and uses Solana accounts as EVM storage. As you may know, Ethereum transactions can be big both in size and also in the amount of computation they do. Neon EVM sometimes cannot process an entire Ethereum transaction in only one Solana transaction, and because of the compute unit limits. And because of this, the EVM state needs to be persisted across multiple Solana transactions. How we do this at the moment, we serialize and deserialize the state of the EVM into a Solana account that is used as input for those transactions. And this repeated serialization, deserialization process by itself consumes compute units and can reduce the amount of actual computation that you can do in that Solana transaction. So let's see if we can actually use the first Solana account in a transaction as a heap in case we have only one Solana transaction. And yes, you can do that. You can just have to redefine the custom allocator to change it the start address of the heap from this to the first account, and to make sure that the Solana account that you give as input for the transaction has a big enough size to fit the entire heap of the program. As a side note, in Solana, the data field of an account can be 10 megabytes big, the upper limit. So now, instead of 256 kilobytes, you can have a heap up to 10 megabytes. But it's not very useful for only one Solana transaction because you have a very small compute unit limit. So basically, you have a big heap, but you cannot compute too much with it. But if you do the same thing across more than one Solana transaction, you can basically persist the heap between iterations. And let's say that we want to have some state that we want to reuse across transactions. We have to avoid the borrow checker because the drop checker, let's say, because basically a normal Solana, a normal Rust program, when you finish it, all the allocations should be dropped at the end of it. We want to avoid that. So let's say that we have a vec of bytes that will be our state. We use the box into row to leak our pointer. We fix the pointer at a predefined fixed address in the Solana account. And why we need it to be predefined is because we need to be able to reinitialize the pointer on the next Solana transaction. And as an example, I put the state pointer at the beginning of the Solana account byte array, and I just started the heap a bit afterwards, after the size of the pointer on Solana, which is 8 bytes. And as a side note, Solana programs do not support static mutable global variables because the Solana memory model doesn't have a segment for global variables. And because of that, why doesn't it have? Because Solana programs only work with a stack and a heap that is local to the running program, and with the data from the accounts. This is the memory model of Solana programs. So you need to do this by hand by storing the state by yourself at some fixed address. Okay, in this example, you can see the state pointer that I chose here. We can see that the state pointer points to a vec of bytes. I also added some assertions here about the values for the heap start address, for the state pointer address. This is the heap length, the maximum heap length that you can have in a Solana program. Basically, it's 10 megabytes minus the size of the pointer before the heap for the state that we want to reuse across transactions. And also here is some code that initializes the heap using the linked list allocator crate. And also, this is the method that function that we use to retrieve the heap in the implementation for the global alloc trait. Okay, let's see a bit another primitives that are not actually very safe from a Rust memory model point of view. The Solana program needs instruction logic to initialize the linked pointer, to use it across multiple transactions, and to deallocate the linked pointer when not needed anymore. And as a side note, theoretically, apart from all the pointers that are reachable from the linked pointer, because we can have a tree of allocations, at the end of each Solana transaction, all the other values should be dropped by the Rust runtime. So I actually checked that with a small program, and it looks like this is the case. So we have, let's say, init state. Basically, we have a state pointer that is null initially. We leak the allocated value on the heap, and we put it into this pointer. So this is the init state. Then we have the state and state mode accessors for the pointer, where we get a reference to the vec that we want to use. And of course, we have the drop state function, which just reinitializes the box from the pointer and drops it. So basically, the allocation is removed from the heap, and the state pointer is set back to null as it was before the first init state. And of course, these are not safe, because if you use this before using this, you will have undefined behavior. So you have to use this in the first transaction, this in between, and this in the last transaction. And your program logic should be very careful about this. What are the problems about what I discussed so far? Because there are also a lot of problems. As I said, if the Solana account data size is less than the heap that you want to use, you will get an access violation by the Solana runtime at some moment or not. Depends on how much heap you use. You can use, of course, if you use only one global heap with a lot of allocations and deallocations across transactions, you can have a very fragmented heap at the end of many Solana transactions. A solution could be to use a second heap with the allocator API to create, which basically duplicates all the allocator API of the original Rust implementation, but it allows you to use it in a safe environment because basically you have the VEC implementation copied, and on top of VEC you can build your own data structures with a custom allocator that you cannot do on a safe Rust for now, and allocate your reused data across transactions only to this heap. There is also the undefined behavior problem, because if you just start a program with a heap that can be corrupted, you have no idea what that program is going to do. And the allocation, this is a bit of an egg and chicken problem. The allocation itself consumes compute units. So maybe using a bump allocator with a heap size big enough might use less compute units than a heap which doesn't leak memory. But benchmarking is needed on a program by program basis in this case. So in conclusion, the Solana runtime memory model is deterministic. This is a very, this is common for all VMs in general and can be used in novel ways. And the first Solana account inside the Solana transaction can be used as a heap. It has a fixed address and can also be persisted across transactions if you need that. And the account heap with this HAP can grow from 256 kilobytes to 10 megabytes. And also everything that I presented here is available as a fork of the Solana program library repo on my GitHub. This is my GitHub and Telegram, and we are also hiring if you're interested into hacking Solana together with us. Thank you for your attention. And I don't know if we have time for questions. Okay. Yeah. Yeah, good question. Basically, we are doing this as part of multiple Ethereum transactions. Basically, while we are doing these iterations, we are executing currently one Ethereum transaction. So the heap for one Ethereum transaction execution will be in one account. And we reuse, we should reuse only the same heap for one Ethereum transaction execution for all iterations. And of course, if you use, you can execute 2 Ethereum transactions concurrently. Basically, that's why we built Neon EVM, because we wanted to be able to execute Ethereum transactions concurrently if they are not, they don't have data dependencies between them. And this is a problem that we are trying to solve now, how you can be sure that someone else doesn't hook into the middle of the transaction and tries to process it. Currently, how we do this is that basically we restart the transaction if we see that there is a modification on the account states that the Solana program uses, and restart it from the beginning. Basically, we have some revision numbers inside those accounts, and if we saw that someone else changed the account since the last time we did it, we just restart the transaction from the beginning. I don't know if this could work with the heap too, but this is how we do it now with the serialization solution. Okay, I don't know if I have. Yeah, that was it. Yeah?
Another question. So, part which is confusing for me is that you mentioned that this rely on undefined behavior, right? How does Solana runtime execution engine can work with consensus and deterministic if it relies on undefined
Mm,
If that makes sense, because like now you can have like multiple nodes that are going to do different things based on the defined data.
this is, I mean, it's not even clear for me yet if we will ever use it in production, because it's very, I mean, we are not currently using it. It's just like a research thing that we discover that we can do. But I'm curious about what the Solana guys would say about this, because it's just, it happens that the first account is fixed, because if that data wasn't fixed, basically you'd have to have all the pointers as offsets in that heap and be able to relocate it in the memory. It's not an easy task. But I don't know, honestly. I'm still trying to understand if we can actually use this. It was more like in the idea of the previous presentation, what we can do with Rust, but maybe you shouldn't. Yeah, thank you.